The Southern Pacific Line crossed the Sierra Nevada through Donner Pass at 7,000 feet. It had been built in the 1860s, expanded through the 1870s and 1880s, and by 1916 it carried most of the freight and passenger traffic between California's coast and the interior states. The route was not optional. Geography left few alternatives. The line threaded through granite ridges, timber slopes, and open saddles where wind moved without obstruction. Winter was anticipated. Every year brought snow. The company maintained snowsheds, miles of timber galleries that enclosed the track, and operated rotary plows designed to cut through drifts. Maintenance crews were stationed at sidings near the summit. The system had handled storms before. Passage was assumed to be a matter of timing and effort, not feasibility. In late January 1916, snow began to fall across the range. It was not remarkable at first. Temperatures dropped, clouds settled over the ridgeline, and accumulation began in the usual places. The cuts where track had been carved into hillsides, the open stretches between sheds, the approaches to tunnels. Traffic slowed but continued. Plows were deployed on schedule. The line remained open, but the snow did not stop, and it did not consolidate into a single event that could be cleared and forgotten. It continued, day after day, in moderate amounts, with wind that redistributed every inch across the grade. The first week brought 12 to 18 inches of new snow across the summit zone. Temperatures hovered between 15 and 25 degrees Fahrenheit. Skies cleared briefly, then closed again. The snow was dry, light, and prone to movement. Plows pushed it from the rails into embankments. Crews shoveled switches and cleared siding access. Trains moved through with minor delays. There was no alarm. This was January in the Sierra. Storms were expected. The infrastructure had been designed for them. Snowsheds protected the most vulnerable sections. Rotary plows, steam-powered machines with forward-facing blades that chewed through snow and expelled it to the side, were positioned at key points along the line. Each plow required a locomotive to push it, a crew to operate it, and a second locomotive behind for additional power and retreat capability. By the end of the first week, the line remained operational. Freight tonnage was slightly reduced, and passenger schedules showed delays of 2 to 4 hours, but the system functioned. Reports from section crews noted snow depth at 30 to 40 inches in open areas, deeper in cuts and depressions. Wind had begun to reshape the surface, filling in spaces that had been cleared the previous day. No warnings were issued. Traffic continued westbound and eastbound. The assumption held: snow could be managed as a maintenance problem, not a systemic threat. The second week brought a shift. Snowfall became intermittent, but wind velocity increased. Gusts reached 40 to 50 miles per hour along exposed ridges and through the saddle at Donner Pass. The wind moved across existing snow cover, lifting particles from open slopes and depositing them in the track corridor. Cuts, sections where the rail line had been excavated below the natural grade, acted as traps. Snow entering from above accumulated faster than it could be removed. Embankments also filled. Where the track had been raised on constructed fills, windward slopes shed snow into the rail bed. The geometry of the line itself became a collector. Every curve, every grade, every transition between cut and fill created a localized drift pattern. What had been inches of depth in the morning became feet by evening, not from additional snowfall but from redistribution. Plows worked continuously. Crews reported progress measured in train lengths per day, not miles. A section cleared in the morning required clearing again by afternoon. The snow was not static. It moved while they worked. Switches became difficult to operate. Ice formed where snow melted briefly during the day and refroze at night. Signal cables stiffened. Telegraph lines remained functional, but communication was slowed by the need for section crews to physically inspect equipment rather than rely on remote indicators. Traffic flow constricted. Trains began to queue at lower elevations, waiting for clearance to proceed. Eastbound consists waited at Colfax. Westbound trains held at Truckee. The line was still open, but capacity had dropped. Passage required coordination, timing, and luck. By the third week, total snowfall since late January exceeded 6 feet at summit elevation. Temperatures remained below freezing day and night. There was no melt cycle. Each new inch of snow added to the total without subtraction. Compaction began. The weight of upper layers compressed the base, transforming loose powder into a denser, more cohesive mass that resisted plowing. Rotary plows could no longer throw snow clear of the right of-way. The space beside the track was already filled with previous clearings. New snow had to be thrown farther, requiring multiple passes. The plow's steam engines labored against increased resistance. Mechanical wear accelerated. Bearings overheated. Blades dulled. Maintenance cycles shortened. Crews worked in shifts around the clock. Men shoveled what machines could not reach. The narrow spaces around switch points, the clearances between rail and snowshed walls, the access paths to water tanks and coal bunkers. Visibility was poor. Daylight was short. Lanterns provided minimal illumination at night. The line began to close intermittently. A plow would clear a section, a train would pass, and within hours the track would be impassable again. Scheduling became reactive rather than planned. Dispatchers waited for reports from the field before authorizing movements. Delays stretched from hours to days. Coastal ports began to report freight backlogs. Goods destined for Nevada, Utah, and points east accumulated in Oakland and San Francisco. Eastbound perishables, produce, dairy, fish, faced spoilage. Inland, raw materials bound for California factories stalled in Reno and Sparks. The rail line was the bottleneck. There was no alternative with comparable capacity. The track's physical characteristics, curves, grades, tunnels became liabilities. On straight, level sections, plows could maintain forward momentum and clear efficiently. But the line over Donner Pass was not straight or level. Grades reached 2.4%, among the steepest on the southern Pacific system. Curves were frequent, with radii as tight as 10 degrees. On curves, snow packed against the outer rail. Plows pushed snow to the side, but centrifugal force and wind brought it back. Clearing required multiple passes at reduced speed. Each pass consumed time and fuel. Grades compounded the problem. Ascending trains lost traction on snow-covered rail. Sand, used to increase friction, mixed with snow and ice to form a slurry that was neither solid nor liquid. Locomotives slipped. Consists stalled. Descending trains faced the opposite problem. Braking was unreliable. Speed had to be kept low, further reducing throughput. Tunnels, 8 of them along the summit section, presented a different challenge. Snow entering from the portals accumulated on the track inside, but the enclosed space prevented plows from expelling it to the side. Crews had to shovel it by hand and carry it out. Tunnel clearing became a labor bottleneck. Progress inside was measured in feet per hour. The engineering that had allowed the line to cross the Sierra now worked against it. The route had been optimized for grades and curves that trains could handle under normal conditions. But snow did not recognize optimization. It filled every depression, clung to every slope, and entered every opening. The track became a channel for accumulation, not passage. Southern Pacific operated 6 rotary plows along the summit section in winter 1916. Each was a specialized machine, a large, circular blade assembly mounted on a railcar frame, powered by a dedicated steam engine. The blade rotated at high speed, cutting into snow and feeding it into a chute that directed it away from the track. A locomotive pushed from behind, providing both motive force and additional steam if needed. Under normal conditions, a rotary plow could clear a mile of track in 1 to 2 hours, depending on snow depth and density. But by the 4th week of the blockade, conditions were no longer normal. Snow depth in cuts exceeded 10 feet in places. The plows encountered compacted drifts that resisted the blades. Forward progress slowed to hundreds of feet per hour. Steam pressure became a limiting factor. The plow's engine and the pusher locomotive both consumed water and coal at high rates. Water tanks and coal bunkers were spaced along the line, but reaching them required clearing track to get there. Fuel and water had to be rationed. Plows operated in shorter shifts to conserve supplies. Mechanical failures increased. Bearings seized from continuous operation in sub-zero temperatures. Blades bent or broke when they struck ice or hidden debris embedded in the snow. Repairs required returning the plow to a maintenance facility, often miles away, and bringing a replacement forward. Each failure created hours of downtime. The plows worked in sequence, advancing as far as conditions allowed, then falling back to regroup. There was no sustained breakthrough. The line was cleared in sections, but the sections did not connect. Traffic could not resume until the entire route was open simultaneously. By early February, several trains were trapped on the line itself. They had entered the summit section during brief windows when passage seemed possible, only to be halted by renewed snowfall or drifts that formed behind them. Retreat was not always feasible. Backing a heavy consist down a steep grade in snow was dangerous. Staying in place was the safer option, even if it meant days of immobility. Crews and passengers waited. The locomotives kept steam up to provide heat, but coal supplies were finite. Rationing began. Cars were kept at minimal livable temperatures. Food was distributed from onboard stores and supplemented by supplies brought in on foot or by handcar from nearby sidings. One consist, a westbound freight, sat for 6 days between Tunnel 6 and Tunnel 8, a distance of less than 3 miles. The train was too long to fit entirely within the snowsheds, leaving several cars exposed to wind and accumulation. Crews shoveled continuously to prevent snow from burying the couplers and undercarriages. The locomotive's coal bunker ran low. A resupply effort required a second locomotive to push a coal car up from Truckee, a journey that took 2 days. Passenger trains received priority for movement when limited clearances became available. Mail and express freight followed. Heavy freight waited. The stranded consists were not forgotten, but they could not be moved until the line ahead was open and secure. Communication with the outside was maintained by telegraph, but the wires were fragile. Ice accumulation broke several spans. Repairs required crews to hike through deep snow to locate the breaks. Messages became infrequent and brief. The Southern Pacific Line used a combination of manual and automatic signals to control train movements. Manual signals, semaphores operated by levers and cables, depended on clear mechanical linkages. Automatic signals used electrical circuits activated by train wheels on the rails. Both systems were vulnerable to snow and ice. Semaphore cables froze. Ice formed inside the conduits that guided the cables, increasing friction and eventually seizing the mechanism entirely. Operators could not move the arms to indicate clear or stop. Manual inspection became necessary. Flagmen were posted at critical junctions to direct trains by hand. Automatic signals failed when snow bridged the gaps between rails, creating false circuits. The system interpreted this as the presence of a train, setting signals to red even when the track was empty. Crews had to physically inspect the rail to verify conditions. Trust in the signal system eroded. Movements proceeded with extreme caution. Switches, the mechanical points that allowed trains to change tracks, were even more vulnerable. Snow and ice packed into the narrow gaps between moving parts. Switch points, which had to align precisely with the rails, became stuck. Heaters designed to keep switches clear were overwhelmed by the volume and persistence of the snow. Crews chipped ice with hammers and applied heat from torches, but the repairs were temporary. Within hours, ice returned. The loss of reliable signaling and switching meant that train movements had to be coordinated manually. Dispatchers relied on telegraph reports and visual confirmation. The system reverted to a slower, older mode of operation, one that had been adequate in the 1870s, but could not handle the traffic demands of 1916. California's ports handled grain, lumber, canned goods, and manufactured products destined for the interior. Nevada, Utah, and the mountain states relied on California for fresh produce, textiles, and machinery. The rail line was the primary conduit for this exchange. When it closed, the flow stopped. In Oakland and San Francisco, warehouses filled. Freight cars sat loaded on sidings, waiting for clearance to move east. Perishable goods, oranges, lettuce, fish spoiled. Cold storage facilities reached capacity. Some shipments were diverted to coastal markets, but prices dropped due to oversupply. Economic loss accumulated daily. Inland mines and mills faced shortages. Timber operations in the Sierra needed replacement parts for saws and boilers. Mining operations in Nevada required blasting powder and steel cable. Without rail access, deliveries were delayed or impossible. Operations slowed or stopped. Workers were idled. Alternative routes existed but were inadequate. The Western Pacific Line, which also crossed the Sierra farther south, was smaller and carried less tonnage. It could absorb some overflow but not all. Highway freight was minimal in 1916, trucks were uncommon, and mountain roads were impassable under snow. Wagon transport was too slow and limited. The blockade exposed the dependency on a single rail line. California's economy was connected to the interior by a corridor only a few feet wide. When that corridor closed, the entire system strained. The Lincoln Highway, a transcontinental automobile route completed in segments by 1915, crossed the Sierra near the rail line. In February 1916, it was impassable. Snow covered the roadbed. Drifts blocked passes. The highway had no snow removal infrastructure comparable to the railroads. Automobiles, still a novelty for long-distance travel, could not move. Wagon roads fared no better. Stage routes that had carried mail and passengers in earlier decades were buried. Mountain communities, small towns, logging camps, mining settlements were isolated. Supplies arrived by sled or ski, or not at all. Communication was limited to telegraph where lines remained intact. The simultaneous closure of rail and road demonstrated the Sierra's dominance. Human infrastructure was temporary and conditional. The mountains allowed passage when conditions permitted and withdrew that allowance when they did not. February 1916 was a withdrawal. Local populations adapted. Stored food was rationed. Woodpiles were conserved. In higher elevations, residents waited. There was no alternative. The snow would end eventually. Until then, movement was not possible. The railroad, with its plows, crews, and institutional momentum, represented the best chance for reopening. But even the railroad was stalled. By mid-February, crews had been working for 3 weeks without achieving sustained passage. A section would be cleared, then close again before a train could traverse it. The problem was not effort, it was timing and volume. Snow fell faster than it could be removed. Rotary plows operated in relays. One plow would advance as far as possible, then withdraw to refuel and reposition while a second plow took over. The handoff points shifted as conditions changed. There was no master plan, only reactive adjustments. Crews worked to exhaustion. Shifts extended beyond 12 hours. Meals were taken in the cab of a locomotive or in a snowshed shelter. Sleep was insufficient. Frostbite and fatigue became common. Several workers were injured, crushed fingers, falls, burns from steam. Medical care was limited to what could be provided on site. The company brought in additional labor from lower elevations. Men were hired on short-term contracts to shovel, clear switches, and assist with plow operations. Pay was higher than standard track maintenance wages, reflecting the difficulty and danger. Some men quit after a few days. Others stayed, driven by necessity or stubbornness. Net progress was difficult to measure. On some days the line was open for a few hours. On others it was closed entirely. Trains moved sporadically. The goal, sustained, reliable passage, remained out of reach. In the third week of February, weather shifted. Snowfall decreased. Wind dropped. Temperatures remained cold, but the absence of new accumulation allowed crews to gain ground. Plows advanced without having to re-clear the same sections repeatedly. By February 22, a narrow corridor was open from Colfax to Truckee. It was single-track, with limited passing sidings accessible. Only one train could occupy the summit section at a time. Scheduling was tight. Eastbound and westbound movements had to be coordinated to avoid conflicts. The first train through was a westbound passenger consist that had been held at Reno for 9 days. It moved slowly, with flagmen stationed at intervals to watch for new drifts or obstructions. The journey from Truckee to Colfax took 8 hours, more than 3 times the normal duration. But it moved. Freight followed. Priority was given to perishables and time-sensitive cargo. Heavy tonnage, coal, or lumber waited. The line was open, but capacity was a fraction of normal. Snowsheds showed damage. Roof sections had collapsed under the weight of accumulated snow. Timbers were cracked or displaced. Some sheds were passable but unstable. Inspection and repair would take weeks. Temporary shoring was installed to keep the most critical sections functional. The blockade was not fully resolved. It was managed. The line operated under constrained conditions, vulnerable to any new storm. Southern Pacific did not publish a comprehensive accounting of the blockade's cost, but partial records and later analyses provided estimates. Freight delays totaled approximately 140,000 ton-miles, goods that arrived days or weeks late, or not at all. Revenue loss from canceled passenger service was estimated in the tens of thousands of dollars. Operational costs increased sharply. Coal and water consumption by locomotives and plows running continuously exceeded normal monthly usage. Labor costs, including overtime and temporary hires, added to expenses. Equipment damage, broken plow blades, damaged snowshed timbers, worn locomotive components, required repair or replacement. Economic impact extended beyond the railroad. California agricultural producers lost crops to spoilage. Inland industries lost production days. Businesses dependent on timely delivery faced inventory shortages. The blockade's ripple effects were diffuse and difficult to quantify, but they were real. The human cost was less tangible. Crews worked under severe conditions for weeks. Stranded passengers endured discomfort and uncertainty. Mountain communities went without mail and supplies. No deaths were directly attributed to the blockade, but the physical and psychological toll was significant. The Sierra had imposed a delay measured in weeks and a cost measured in hundreds of thousands of dollars. The line had not failed permanently, but it had failed functionally for an extended period. That was enough to warrant attention. After the blockade ended, Southern Pacific reviewed its winter operations. The event was not unprecedented. Severe winter closures had occurred before, but the duration and persistence of the 1916 blockade highlighted vulnerabilities. Snow was reclassified internally from a routine maintenance challenge to a systemic risk. Planning shifted. The company expanded snowshed coverage, adding new sections and reinforcing existing structures. Additional rotary plows were purchased and stationed along the line. Crew housing was improved at high-elevation sidings to support longer deployments. Telegraph and signal systems were upgraded with better cold weather insulation. Switch heaters received more powerful designs. Stockpiles of coal and supplies were increased at key locations to reduce dependency on continuous resupply during storms. The changes were incremental, not transformative. The line's geometry, its curves, grades, and tunnels, could not be fundamentally altered without massive reconstruction. The route remained vulnerable. The improvements reduced that vulnerability but did not eliminate it. The blockade entered company records as a reference point. Future winter operations were measured against it. Crews knew that snow could close the line for weeks, not days. That knowledge shaped decisions. By March 1916, the Sierra was clear enough for normal operations to resume. Traffic returned to regular schedules. The line was open, but the memory of closure remained, a quiet reminder that passage was conditional and that the mountains decided when and whether trains would move.